Let's now turn our attention to the idea of limits. Now, all of calculus is built on the idea of limits. However, just because it's crucial to calculus does not mean that limits are super difficult. All a limit is it asks the question, how is the output, or said in another word, the function value, behaving near a certain input value? And I'm going to underline the key distinctions here for a limit. One of the key differences is the idea of near input. Normally, if I told you that we had a function f of x is x plus 3, the kind of process we would normally do is say, well, let's see what's the value of the function at 2. In that place, we care about the value of the function at an exact input value. So I would plug in 2, and I'd say the function is exactly at height 5. And the difference here is for limits, we actually don't care about the actual input values corresponding output value. We care about all of the input values very, very near to that input value. How are they behaving? So keep this in mind, this initial distinction. Everything to this point in your mathematical education has been dealing with the actual function value at an exact point, whereas limits care about a value near to a point. And we'll soon see this explanation in our next example. So let's consider that we start with the function f of x. So here we see x is our input, and the corresponding output is given by the function value f. And we see our graph here. And just to review, we know that this open circle represents a hole. So if we were asked, what is the output value when the input is 2? So this is saying if the input is equal to 2, what's the output value equal to? So let's look. We go over to x value of 2, and we look up, and we see that although we'd normally expect there to be a value at height 3, there's an open circle, which means that there is no value here. That's the idea of a hole. So we would say the function value at 2 does not exist, or you could say that it's undefined. Now focus on this. If all you were told is this and you couldn't see the graph, pretend the graph is gone, do we see that this gives us very little information other than at that exact point? At 2, there is no point. But it doesn't tell us what was happening very near to 2, because actually if you look at the graph, there's a trend, right? For instance, consider the x values here to here. For every value between these x values that I've marked a little before 2, a little after 2, there are corresponding output values. And do we agree that as I choose input values closer to 2, the output values are increasing steadily up to 3? And as I choose input values after 2 and I go closer to 2, the output values are steadily decreasing to 3. So while there is not a specific output value at the exact input 2, there is a trend to the corresponding input-output values as we get closer and closer to the x value of 2. How are the output values of f of x behaving as we near the input value of 2? So in this case, let's look. Here, I'm not at 2, but I'm kind of close. I'm here. Pick a closer input value. Let me actually zoom into the graph. So I'm going to pick a input value close to 2, and I see there's my output value. Now the idea here is we care about a trend. So you do this over and over with the goal of getting closer and closer to 2. So we're successively picking input values closer to 2, so I move closer, the output value increased. I move closer, the output value increased. And it didn't just generically increase, it's increasing, but by lesser and lesser. It seems to be the closer I moved towards the input value of 2 through values smaller than it, do we see their output values are going to keep kind of condensing around the output value of 3. The same thing occurs if I pick output values to the right. So I pick an output value to the right, pick another input value closer, see that the output value decreases a little, continue this pattern, And we can imagine that I could get very, very, very close to 2 from the left and right. And what happens is my output values are going to shrink closer and closer around height 3. That's the idea of the limit. And the way we would write that is that the limit as x approaches 2 of our function f of x equals 3. So that tells us that as you get very close to 2, the output values are getting very, very, very close to 3. However, we do have it that at 2, the value is undefined because we have that hole. So this was our first limit calculation here. So let's just write this in. How are the output values for this graph behaving near the input of 2? What we're going to say is as we get closer and closer to the input value 2, the output values follow a pattern of getting closer and closer to 3. And you see that closer and closer mention is showing this progression or this trend. Now this statement is informally in words describing the idea of a limit. The way you would write the limit is we always have the LIM that's indicating the concept of the limit, that is, let the x values get closer to some value and then see what's the trend in the corresponding output values. So we write limit to indicate that idea, and then we say where are the x values getting closer and closer to. In this case, the x values are getting closer and closer to 2 of what? The function f of x. So as the x values get closer and closer to 2, the output values are following the pattern of getting closer and closer to 3. So we would say this limit is 3. Now, as we were just introducing the idea of limits before, we just naturally started talking about, we're getting close to 2, but I could get close to 2 from values lower than 2, for instance, like 1.9, 1.99, 1.999. That's the idea of getting closer from the left, or I could get closer to 2 through values greater than 2, like 2.1, 2.01, 2.001, and that's what distinguishes for us the idea of the left-hand limit and the right-hand limit. Now what we saw earlier, when there's no indication of left or right, is implied to be the two-sided limit. The only distinction in the notation is this superscript. It's still LIM to represent limit, LIM, you still describe the function, but instead of just saying x goes to 2, we might use the notation x goes to 2 superscript minus sign to indicate from the left, or in an example, x goes to 2 superscript plus sign to indicate it's going from the right. So for a left-hand limit, you see what's happening to the output values as the input values are getting closer and closer from the left or through lesser values, and this is the notation for that. And for a right-hand limit, you see what happens to the output values whenever we approach the input values from the right or through greater values. And the only distinction is the superscript, and if there is no superscript, then it's the two-sided limit from both left and right if there's a pattern. Let's look at our next example. We have a function graphed here, and there's some odd behaviors to this function. We see that we've got a hole, which is redefined up here at -6. We have a vertical asymptote at -4. We've got this disconnection where before x equals 6, our graph was below the x-axis. After x equals 6, it's above the x-axis. So this is our function f of x, and we're asked to evaluate these two limits. Now keep in your mind, the main thing you want to remember about limits is limits are not necessarily function values. Function values care about the behavior at a point. Limits care about the behavior near to a point. Now, what x value are we interested in for our first limit? Take a moment to look at the notation and think, what x value do we care about? We care about the x value of 6. That's a positive 6. And do we see this superscript notation of a little minus? Now, since it's in the superscript, it's not a negative symbol, right? It's just saying the limit as we approach from the left of 6. So let's find 6 on our graph. We have it here. So we're going to choose values smaller than 6. And we're going to get closer and closer to 6 and see what happens in the trend of output values. Let me zoom into this portion of the graph. So we know limit cares about a trend, not the value itself, so I'm going to pick a x value close to 6. So we don't pick over here, that's not close to 6, right? We're doing a limit, so we're getting closer and closer, so maybe here. That's an input value. I go down. Its corresponding output value is there. And then a limit, we do that for a progression of values, right? So we then get closer to 6 from the left. And I see its corresponding output value. What do we notice? It's gradually increased a little bit. But as I keep choosing closer and closer input values to 6, I see that I'm going to just move up this line more and more, but I'm not going to just keep increasing forever, right? No, there's a definite stopping point. As I get closer and closer to 6, the output values are getting closer and closer to this fixed point here at 6. So the closer you get to the left from 6, the closer the output values go to -1. So that's how we would answer this limit. This equals -1. Now for our next limit, we would read this as the limit as x goes to +6 from the right of the function f of x. So we know we care about +6, but we care about it as we get closer from the right through larger values. Let's zoom into this graph. As I picked closer and closer input values from the left and considered the pattern in the output values, take a moment to pause the video, and since we're approaching 6 from the right, pick closer and closer input values to the right of 6 and see what happens in their pattern to evaluate this limit. I recommend you pause the video now, work on this, and then unpause to check your work. So I'll choose input value somewhat close to 6, and I'll just get closer and closer. So at this input value, the output is here. I just looked vertically above the graph. As I choose a closer input value, the output has decreased slightly. And if I continue this pattern, what I notice is the closer my input values get to 6 from the right, I'm going to continue to decrease along this straight line, but I don't just decrease forever, right? I decrease to a point, and that point is when I reach this hole, which is at halfway between 1 and 2, so 1.5. So from the right, as the input values get closer to 6, the output values decrease steadily to 1.5. So this limit is 1.5. And what we notice is we just calculated two limits about the same 0.6, but one was from the left and one was from the right, and we got that their limit values don't agree, which matches our graph because we see that right about the 0.6 there's this big jump. So the values before 6 were acting very differently than the values after 6. Now in this case, if the one-sided limits are not equal, then we say that the general limit, which is implied to be the two-sided limit, does not exist, and you can abbreviate this D and E. So the way we would see that written is that the limit as x approaches 6, notice there's no superscript, so that's implied to be from both directions. This limit does not reach an agreement in behavior. From one side it's going to -1, from the other side it's going to 1.5. Since they don't agree, then the overall limit does not exist. Now all of this should be distinguished from function value, which is something that we've been calculating for years, right? The function value is at 6, what's the value of the function? And we see since there's an open circle above but a closed circle below, we would take the closed circle value. So at 6, the output value is at -1. But we know limits talk more about the behavior near to the point. Now we'll soon go back to the graph, but I wanted to zoom in so that you could clearly see our next two limits. Take a moment to think about how you would read these. Now I would read the first one as the limit as x goes to -6 from the left of the function is equal to, that's what we have to figure out from the graph. The limit as x goes to -6 from the right of f of x is equal to, and now we just need to turn to the graph. So we've got the left-hand limit about -6 and the right-hand limit about -6. We find -6 as our input value. Here we have it. Take a moment to consider the left and right hand limits. I recommend that you would pause the video, calculate these two limits, one from the left and one from the right at 6, and then unpause to check your work. Now to evaluate the limit from the left, we visualize finding -6, and I'm going to pick ever closer and closer input values, and I'm going to see what's the pattern in their corresponding output values. Now here my input value corresponds to that output value, and as my input values get closer to -6 from the left, my output values will move along this curve up to this point at the hole here. So they're going to reach the value that is halfway between 1.5 and 2, 1 and 2, which is 1.5. Now the limit as we approach -6 from the right would be going through larger input values. And I say what's happening as my input values get closer to -6, the output values correspondingly decrease along this curve, again to the stopping point at the hole, which is at height 1.5. Now in this case, since both the left and the right hand limits agree, we would write this as the two-sided limit, where it's just the limit as x goes to -6, no left or right indicated, is 1.5. So if the left and right hand limits agree and are equal, you automatically know the two-sided limit. And just for practice off to the side, I want to give everybody a moment to try to evaluate the function value at -6. Remember, function value is not necessarily the same thing as limit. Here we would get at -6, the function value is here, right? Because we had an open circle there, so we look for the filled-in circle, which would be at height 3. So we see that in this case, our limit greatly disagrees with our function value. So limit and function value do not have to be the same thing. We found that both the left and the right hand limits at -6 were 1.5. And we noticed that these one-sided limits agreed, and if both the single-sided or one-sided limits exist and are equal, then you automatically know the two-sided limit agrees with them on that value. Now just because the limit exists does not mean the limit is equal to the output value. As we saw earlier, the actual output value at -6 was height 3, which was different than its limit values. Now in each of our two previous examples, we were given a graphical description of the function, and based on this graphical description, we could identify the limit. And what we did in those cases is we found a pattern. As our input values get closer and closer to some value, what happens to the output values? Is there a trend that we notice? And this is easier to do when we're given a graph, but we could still follow the same basic principle even if we're not given a graph by constructing a well-made table of values. Sometimes we're given a description of the function. As we were here, our function is x squared minus 1, all divided by x minus 1. And we're asked to find the output value when the function takes on the x value of 1 if it exists, and then after that we need to consider the limit as x approaches 1. Let's start with the first one. As I plug in the value 1 to the function, everywhere there's an x I'm going to plug in 1. That gets me 1 squared minus 1 over 1 minus 1. That's 1 minus 1 over 1 minus 1, which is 0 over 0. Now anything dividing by 0 is a problem, so we know this automatically. You could phrase it as does not exist, or you could also say it's undefined. So at the input value of 1, our function does not exist. There is no output value for the function input value of 1. Just because at a point, though, it doesn't have a value, does not mean there might not be a trend of values very close to the input value of 1. And that's the idea of the limit. So here we're asked what's the limit of the function f of x as x approaches 1 for a function x squared minus 1 over x minus 1. And if we had a graph, what would we do? We would look at the x value of 1, and we would say what happens as the x values get closer to 1 from the left and the right? What's happening to the trend of output values? And we can do this through a table. Now if you look at my table, see the pattern of x values I've chosen. First of all, it's based on what input are we approaching in our limit. We're approaching 1. Now we want to approach 1 both as we go through smaller values from the left and larger values from the right, and we want to get very close to 1. So for instance, I choose 0.99, and then my next closer value from the left, 0.999, 0.9999. That's approaching from the left. That would be like the left-hand limit. If there's a trend that emerges here, that's our left-hand limit. And then I choose values that are larger than 1, starting at 1.01, and then getting closer. These 3 points are trying to get us the pattern for approaching from the right. So if there's a trend here, and a trend here, and they agree, then that's going to be the idea of our two-sided limit. So what we would do is in our calculator, we would, for the first one, type in 0.99 squared minus 1 over 0.99 minus 1. I recommend you get a calculator, pause this now, and find these values, following the same formula that we've shown here, just for the different input values, and then unpause to check your work. Now as we calculate the first one, we should get 1.99. And as you calculate the remaining table values, you would get as x is 0.999, the output value is 1.999, and then you could see the remaining values in the table. So now we've created a carefully constructed table values that get closer to our input values through values smaller than it and values larger than it through a steadily kind of closer and closer approach. We now look at the pattern of the output values. So as the input values get closer to 1 from the left, do we see the output values are increasing, getting closer and closer to 2, 1.99, 1.999, 1.9999. As the input values are getting closer to 1 from the right, the output values are decreasing down closer and closer to 2. So based on this, we see that both from the left and the right, the output values are getting closer and closer and closer to 2. So we should be able to estimate that our limit is 2, which is exactly the case here. So in this example, even though the function did not have a value at 1, there is a trend to its behavior near this point, and the trend is that the behavior of the points near it are getting closer and closer to 2. Now if we were to graph this, this expression would represent the straight line of slope 1 that passes through the y-intercept of 1. The only distinction is at the point 1, we're undefined. But we see that as the input values get closer and closer to 1, the output values get closer and closer to 2. Now you won't be asked to figure out how to graph this from this section, just be able to make a carefully constructed table, but all of this information can be recalled from earlier when we learned how to graph rational functions and we dealt with holes and things like that. Now sometimes we have limits that do not exist. Here I've shown a graph of sine of pi over x, and we see it has kind of normal behavior at first, but then what do we notice is it starts oscillating faster back and forth, and this middle section of almost solid color is showing oscillation that is happening faster and faster and faster and faster. In fact, the closer we get to 0, the more wild this oscillation becomes, to where if you kept zooming in and zooming in and zooming in, you'd keep seeing these waves more and more and more. And you can see that maybe a bit more clearly through the table. Notice my x values are approaching 0 from the left. They start at negative 0.1, negative 0.03, negative 0.007, until we get very close to 0 with negative 0.000065. But what's happening in the output values? At first the output value is 0, then it's 0.86, so it jumped positive, then it's negative 0.434, so it jumped negative, but it seems like we're getting smaller. But then it jumps positive again, and then it jumps negative even greater. So there's no real pattern to these output values. They're not getting closer and closer to anything. There's no pattern as we approach 0 from the left. Similarly, as you approach 0 from the right, there's still no pattern. It's just jumping back and forth, back and forth. So in this case, we would say this limit does not exist, because there's no pattern in its behavior as the x values get closer and closer to 0 from either the left or the right. Now in our final example, we've been given a graphical description, and we're asked to calculate the following limits. Take a moment to think about how you would read this. It would be the limit as x approaches negative 3 from the left, that's what that superscript minus is, of the function. So let's find negative 3, that would be here at this vertical asymptote. Now as we approach negative 3 from the left, try to visualize where that is on the graph. Approaching from the left is approaching through smaller values, so it would be saying like pick input values that get closer and closer to negative 3 from here. What's happening is that the output values are getting higher and higher and higher, and there's no end to this trend. In fact, if you look, the closer you get to negative 3 from the left, the higher your output value goes. And since we have this asymptote here, this is never going to stabilize. It's just going to get higher and higher and higher forever and ever. So this would be a case that we would say the closer we get, the larger the output becomes without bound, so the limit is infinite. And since it's going in the increasing direction, it's a positive infinity. Whereas if we investigated the limit as x approaches negative 3 from the right, we're now going to choose x values that are still getting closer to negative 3, but through values greater than it. So I see what's happening to the trend of output values. The output values are getting smaller and smaller and smaller, and they're approaching this vertical asymptote, which tells me that they're just going to keep getting smaller and smaller forever and ever. So since there's no bound to their decrease, we would say the limit is negative infinity to show that they're decreasing forever. Now the limit as x approaches negative 3 from both directions, see there's no superscript, so it's implied the two-sided. Well, all you have to do is you look at the previous one-sided limits and ask if they agree. If they agree, then the two-sided limit is just what they agree on. If they disagree at all, then the limit does not exist. So in this case, in approaching from the left, we go to positive infinity. Approaching from the right, we go to negative infinity. Those are definitely not in agreement, so we would say this limit overall does not exist. And then our final question has to do with limits as x does not approach a finite value, but as x goes to negative infinity and positive infinity. And the limit as x goes to positive or negative infinity is just asking you about the trend of the function overall as we go to one or the other. Let's start here. X is the horizontal axis, right? And if x is going to negative infinity, we're going out this direction forever and ever. So we need to look at the graph of the function and say what trend has already been set. So let's look at some of our x values farthest to the left that we have. So for instance, at maybe -8, do we see the output values here? But as we get farther to the left, at -9, the output value's here. At -10, it's here. And then it continues, and in words, couldn't we describe it to say, it seems like the farther out we go in output values, we're just going to keep approaching this horizontal asymptote at -5. So the idea is, the farther and farther out I go, the closer my function's going to get to this horizontal asymptote. So they're going to trend steadily closer and closer to -5. So the output values are steadily decreasing, but by less and less, and approaching a fixed value of -5. However, as we approach x goes to positive infinity, that's going out here forever. And in that case, we would say, what's the pattern that's been set? Well, you look at larger x values that we have in that direction. So for instance, here, we've got our output value there. And we see the progression of output values is they seem to be just continuing along this straight line. And we know the straight line is going to increase forever without bound. It's not approaching some limiting value or horizontal asymptote. It's just going to get higher and higher and higher. So for instance, if I look out at 1,000, it's higher. 10,000 gets even higher, and it's going to keep getting larger and larger without bound. So we would say this limit is infinite, because now the output values are approaching infinity. So let's just recap from this lesson. We have seen how to deal with limits if we're given a graph. We know limits care about the behavior of output values near a certain input value, not necessarily at the exact value of the input. We also know that if we're given a function, we can create a carefully constructed table to evaluate limits as well. And then finally, we looked at what does it mean to have limits that are either going to infinity or limits where the x values are going to positive or negative infinity. How do we determine those limits?